Welcome, students. This is your instructor, Sandra Hindo. I would like to welcome you to Lean Six Sigma Yellow Belt. If you're sitting in this class, you automatically got access and lecture to all of the material contained within the first course, Lean Six Sigma White Belts. That is automatic. So do pause this video if you have yet to review the Lean Six Sigma White Belt material. And do watch all of the Lean Six Sigma White Belt lectures if you are new to that material. But if you've already gone through lots of Lean Six Sigma training in the past and you are confident to start in the yellow belt, then you do not have to do it. Because after all, in this course, you will only be tested on the yellow belt material. In this course, we will be covering Six Sigma statistical definition, measure phase deliverables, measure phase tools, and introduction to statistics and distributions. Here are the expectations. With respect to the material, please take the slide deck slowly and fully enjoy the experience of being in Lean Six Sigma White Belt. Do take notes. While the end of belt exam is open book, open notes, open PowerPoint, I encourage you to take notes while sitting in the course. Pass the exam. In order to earn your certification, you have 2 attempts to pass a 50-question exam, answering a minimum of 80% questions correct. That means you need to answer 40 questions correct out of 50. Lastly, upon passing the end of belt exam, you will receive your digital certificate. When you email me, it's very important that you spell your name exactly the way you want it to appear on your certificate. Do examine the spelling carefully before emailing me. Make it truly worthwhile by cooperating. If this is a live session, sessions usually start around 9 a.m. and end at 5 p.m. You have a 1-hour break for lunch. In the breakout rooms, there's usually coffee and tea. Feel free to use the restrooms when needed. In order to make the most out of the course, try to stay away from your cell phones, but obviously if there's emergencies, feel free to use them. Taking notes is important. Try to avoid the desire to do an internet search or check email. You'll gain the most out of this class by being fully present on the material that's being shared with you. Questions are always welcome, always useful. Knowledge truly does equal wealth, and that's why you're sitting in this course today. Focus and concentrate. Accuracy and precision both matter. Targets are for you. Here's the agenda for the Lean Six Sigma Yellow Belt course. Six Sigma statistical definition, exercise pertaining to calculating sigma values, measure phase deliverables, process capability study, measure phase tools, process capability, measure phase tools, gauge R&R, measure phase tools, gauge R&R methods. In a wide range of professions, decisions must be made and conclusions must be reached. Data must be collected to throw light on these issues. Statistics is a body of techniques that provides useful information to decision makers from such data. An engineer is someone who solves problems of interest to society by the efficient application of scientific principles. They accomplish by either refining an existing product or process or by designing a new product or process that meets customers' needs. Consequently, engineers must know how to efficiently plan experiments, collect data, analyze and interpret data, and understand how the observed data are related to the model they have proposed for the problem under study. The field of statistics deals with the collection, presentation, analysis, and use of data to make decisions, solve problems, and design products and processes. Because many aspects of engineering practice involve working with data, obviously some knowledge of statistics is important to any engineer. Statistical techniques can be a powerful aid in designing new products and systems, improving existing designs, and developing, and improving production processes. We will be taking a look at Six Sigma statistical definition. Probability and the normal distribution. For example, if we had a sample of ratings from 100 customers, what could this tell us about the feelings of the entire customer base? How precisely would this measure the true overall customer perception, and how certain would we be of the answer? How much would customer satisfaction need to change before we could detect it with any certainty? These are the kind of questions we will be able to answer using probability. Let's carefully examine this slide. Probability and the normal distribution. Probability is the study of likelihood. When we use samples to estimate population parameters, we cannot be certain that our answers are correct because we do not have 100% of the information. Therefore, we need to be concerned with the likelihood that we are correct. Probability provides methods that help us quantify the certainty of our answers. We can also use these concepts to develop some powerful methods for analyzing and understanding data. Here is a probability example. In a roll of an unbiased die, what is the probability of rolling a 5? What about a 5 or a 6? An odd number? Any number except 2? A number above 5? All numbers. Let's look at this. A single 6-sided die is rolled. What is the probability of each outcome? What is the probability of rolling an even number, of rolling an odd number? Here are the answers. The probability of rolling a 5 is 1. The probability of rolling a 5 or a 6, 2. An odd number, 4. Any number except 2, 5. All numbers, 6. Probability. Distributions provide probability. And right here, as you can see, this is the frequency, and these are the values. The frequency at 0 is about 40%. The frequency of 3 is a little less than 10%. The value at 1, around 19%, and so on. What is the probability of receiving an order within 60 days of contact? Let's look at this very carefully. Within 60 days of contact, what is the probability? Ooh, it's really high. It's around 400 to 500. But the spread of when you receive the order is wide and varied. The spread is called variability, also known as variance. Let's assume the data collected from a process is as followed. Now, everything that's going from left and right, let me use my highlighter. Everything that's going from here to here, here to there, that is called variability. So there's a lot of difference when we look at what is the variability of receiving an order within the first moment that you get contact with a customer, okay? There's a lot of variability here. From here to there, okay? What is variability? Variability is the successive observations of a system or phenomenon do not produce exactly the same results. We all encounter variability in our decision-making process. Variability is often measured by standard deviation for distributions that are systematic about the mean, like normal distribution. The units of measurements for the variance are the square of the original units of the variable. Since the bar always sums to 0, we use a measure of variance that changes negative values into non-negative quantities. Ideally, when you are working on a Lean Six Sigma project, what this means in the real world is that you want to have consistency from the moment that a customer makes contact with you and when a customer receives an order. Being high in both reliability and reproducibility is truly at the heart of a successful Lean Six Sigma program. Practical probability. As we just saw, we can begin making simple probability statements using histograms. However, if the questions ask for information that does not coincide exactly with the cell bounds, our ability to estimate probabilities becomes compromised. In addition, histograms provide an empirical answer, but we can provide both more precise and more generic answers if we look at the underlying theoretical distributions. We can begin making simple probability statements using histograms. Histograms provide empirical answers. We can provide more precise answers if we look at the underlying theoretical distributions. We begin by looking at the normal distribution. So we're taking a look at this. This is the basic probability model for process analysis. Ideally, we want most of our observations and data to be centered. This way we can ensure that we're somewhere in the middle of the customer's lower and upper specification limits. So basically in normal talk, this means we are meeting the customer's requirements. We're not too high and not too low. Let's begin with an easy example. What percent is shaded? This looks 50% to me, right? This is a normal distribution. A bell-shaped curve that is symmetric about its mean. The normal distribution is the most common statistical distribution because approximate normality arises naturally in many physical, biological, and social measurement situations. Many statistical analyses require that the data come from the normally distributed populations. For example, the heights of all adult males residing in the state of Pennsylvania are approximately normally distributed. Therefore, the heights of most men will be close to the mean height of 69 inches. A similar number of men will be just taller and just shorter than 69 inches. Only a few will be much taller or much shorter. The mean, which looks like a U symbol, and the standard deviation are the two parameters that define the normal distribution. The mean is the peak or the center of the bell-shaped curve. The standard deviation determines the spread in the data. Approximately 60% of observations are within plus minus 1 standard deviation of the mean. 95% are within plus negative 2 standard deviations of the mean, and 99% are within plus minus 3 standard deviations of the mean. This right here that you're looking at is a normal distribution. Generalized probability. Pretty easy, huh? What if we want only a small part of the distribution? Now, what percent is shaded? This is much less. I'm going to go at about maybe 20% is shaded. To answer these kinds of questions, let's find out more about the normal distribution. Normal curve and standard deviation. The normal distribution takes different forms and has two characteristics. For us to understand this, we need to see and look at this: standard deviation, and standard deviation. The most common measure of dispersion, or how spread out the data are from the mean, is known as the standard deviation. While the range estimates the spread of the data by subtracting the minimum value for the maximum value, the standard deviation roughly estimates the average distance of the individual observations from the mean. The greater the standard deviation, the greater the spread in the data. Standard deviation can be used as a preliminary benchmark for estimating the overall variation of a process. The standard deviation is calculated by taking the positive square root of the variance, another measure of the data dispersion. Standard deviation is often more convenient and intuitive to work with, however, because it uses the same units as the data. Let's use normal words and what you really need to understand from this slide. Your customers have data ranges that you are required to meet. Who must you listen to? The customer always. So the customer tells you when you're making that standard cup of latte, they want it to be between 1 minute and 45 seconds and 2 minutes and 40 seconds. So you need to stay within the customer specification limits. And as long as you stay within here, or within here, or within here, you are fine. But what this is telling you that this is only one standard deviation to the left and one standard deviation to the right. So it's much more tight. That means those baristas are making the drinks very close and very consistently. But you don't need to just be at one standard deviation. You can be at 2 standard deviations and you're still fine. That means you're 2 standard deviation away from the ideal time it takes to make that hot latte for your customer, okay? And then you're 1 and then 2 standard deviations away from the mean. But you can also be 3 standard deviations away from the mean. This gives you 1, 2, 3 until you reach it. And then 1 standard deviation, 2 standard deviation, 3. So it gives you more room to have variation in the time it takes the barista to make your grande hot latte. ideally you need to be careful, okay? Because let's say right here, this is the minimum 1 minute and 45 seconds. You don't want to start having data points that are here and here and here. You got to be careful. Because if it's only taking you 20 seconds to make a hot latte for your customer, there's something wrong. That quality of that drink, it's going to taste funny. There's going to be some steps that were missed. And that's all the standard deviation means. Don't even get caught up with what you're seeing here. Well, you need to know if there's any data points that are here, 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 you're in trouble. Because now you're out of range with what the customer is expecting of you. That's all this means. But let's say this point right here, this point is the maximum time that the barista is allowed to make that drink, that standard hot latte, grande latte. Let's say that was, what did I say? 2 minutes and 40 seconds. And these are all just fun numbers that I'm throwing out here. If all of a sudden your baristas get comfortable and they're at this point, then 1 or 2 times or multiple times they start producing the drink somewhere here, in here, in here. It might take them 3 minutes, and another time it's 4 minutes. So you want to be careful. You want all of your dots to be within these parameters. And your customer is the one who's going to tell you if they're going to allow you to be at a 3 standard deviation or 2 or 1. That's not up to you. That's your customer. And your job is to meet your customer's requirements. So what is your customer going to have? Like we learned about in the Lean Six Sigma white belt material, is that they're going to specify something known as a LSL. LSL is the lower specification limit. That's the lowest number they're going to expect from you. And they're going to provide you with an upper specification limit known as USL. And in this case, it was 2 minutes and 40 seconds. So basically, your customer is letting you know that when you make that grande latte, you need to be between 1 minute and 45 seconds to 2 minutes and 40 seconds. As long as you're within that range, that you're meeting your customer specification limits and you're going to be in good shape. That's all this distribution means, that you wanted all your data points, you want them to fall within here. And again, who specifies whether they want you at the standard deviation 1? That's very tight. Or whether they want you at standard deviation 2, a little better, or standard deviation 3. Right? If it's a robotic process, if it's not a lot of humans involved, then obviously your process would be more tight. The more training that you do among all of your employees, the tighter the process. And when I say the tighter the process, what I mean by that is the numbers are going to be more close to that ideal point, the mean. Probability and the area under normal curve. The standard deviation is calculated by taking the positive square root of the variance, another measure of data dispersion. Standard deviation is often more convenient and intuitive to work with. However, because it uses the same units as the data. For example, if a machine part is weighed in grams, the standard deviation of its weight is also calculated in grams, while its variance is calculated in grams too. In a normal bell-shaped distribution, successive standard deviations from the mean provide useful benchmarks for estimating the percentage of data observation. About 95% of the observations fall within 2 standard deviations of the mean, shown by the blue shaded area. About 68% of the observations fall within 1 standard deviation from the mean. -1, 2, +1. And about 99.7% of the observations would fall within 3 standard deviations of the mean, -3, 2 plus 3. The symbol S sigma is often used to represent the standard deviation of a population, while S is used to represent the standard deviation of a sample. Variation that is not random or natural to the process is often referred to as noise. Let me pull out my little highlighter here. Let's see, it's working good. Yeah. Probability in the area of the normal curve. This is very intimidating for my students, and that's why I use the hot latte example, okay? So I'm going to use that, and then I'm going to be creative and just give you one more example and tell you what you really need to understand from this slide. So a popular coffee chain, this is just a fictional example, they come up with a standard operating procedure. They test everything out, and they said to make the perfect cup of hot grande latte, it takes anywhere from 1 minute and 40 seconds or 1 minute and 45 seconds to 2 minutes and 40 seconds, okay? So this number here is 1 minute and 45 seconds, and this number here is 2 minutes and 40 seconds. As long as a barista and then the baristas continue making all the drinks and their data points are falling here, 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 all within this area, the baristas get to go. You can then say that the process is in statistical control. But if all of a sudden they're making drinks and it falls out, it falls below the customer's lower specification limits, or it falls above the customer's upper specification limits, then you have a problem. So if you're making the drink in 20 seconds, 50 seconds, 1 minute, 20 seconds, then obviously you're not following the process steps. Obviously you're rushing. You didn't do some measurements correctly. You skipped some steps. You forgot some steps. You made the wrong drink. Who knows what's going on? Or if you're all the way up here, there's also other issues. That means you're getting distracted. You didn't put the milk in the right place. There's a huge line. There's a lack of efficiency. Then there's also problems here. And your customer is going to tell you exactly what they're okay with in terms of their lower specification limit number and their upper specification limit number. The customer decides that, not you. Another example is the auto manufacturing when they're putting in the windows. There's only a small room for variation. And then when you fall outside of the limits of that small room of variation, that window will no longer do its job, and the vehicle cannot get to the next process. It fails inspection. There's only so much variation that is allowed for the window to be able to be properly placed when making a vehicle. But even if you are just a few centimeters away from that, then that process fails. It's going to fail inspection. You're going to have problems. So in anything that whether you're dealing with a car part, or you're dealing with furniture, or a computer, or a service, or an application, for that product or that service to work, it needs to be within your customer's upper and lower specification limits. It all needs to be within all the data, all the dots need to fall within this process. And that's why we use Lean Six Sigma to create a cleaner process. And the more tight that you are in the center, the better off you're going to be. Because you don't want to get all to this point where you're so close to reaching this point, then all your dots are going to be here. You're so close to reaching this point, and then all your dots are going to be here. You don't want to get to that point. The empirical rule of the standard deviation. Rule 1. Roughly 60 to 75% of the data are within a distance of 1 standard deviation on either side of the mean. Rule 2. Usually 90 to 98% of the data are within a distance of 2 standard deviations on either side of the mean. Rule 3. Approximately 99 to 100% of the data are within a distance of 3 standard deviations on either side of the mean. Probability and the process spread. Week 1 process, the mean is what? It's at 10. And the standard deviation, 1, 2, is at 2. And then to the right, standard deviation is at 2. So the process step, in this one, they're saying, well, the lower specification limit, the lowest number could be 5. And this higher number is 15. And any dots that are here or any dots that are here, the process is now out of control. Now, week 2 process, this is probably after you do the improvement plan, okay? Your improved mean is 10. That's ideal, right? And now your standard deviation, 8. 12. So this is before the improvement plan in your Lean Six Sigma project, and this is after your improvement plan. This was at week 1. And this was, then you implement your improvement plan, right, as a Lean Six Sigma practitioner. And these are your results for week 2. So this range, while there were still data points, and I'm not gonna say it's 4 because it's right here, it's 5, right? While the data points during week 1, we were willing to accept dots, also known as data points. We were willing to accept being anywhere, the dots ranging anywhere from 5 to 15. Well, let's what's the range? If it's 5 to 15, then we're willing to accept a range of 10, right? Because we take the maximum, subtract it by the minimum, which is 10. But now you came in as a Lean Six Sigma practitioner. You got down to business. You created the process maps. You cleaned up your process with your team members. And look at the results of week 2. Now, all the data points are between 8 and, let's say, let me look at this carefully. Let's say 12, or almost 12, but let's just say 8 to 12. I think that's what they mean. 8 to 12. Now we're going to take the new range. So we're going to take the maximum 12 and subtract it by the minimum. And that's 4. 4. So this range is at 4. And this range, let me remember what I said, 5 and 15 is at 10. So let me ask you a question, students. Where do you want to be if you were the one leading this Lean Six Sigma project for your team? Do you want a range of 10 or do you want a range of 4? Take a moment to ponder that. You are correct. The answer is you want to be of range 4 because this one is a tighter process. Do you know what the word is for a tight process? It's a process that is in statistical control. That process is stable. When a process is stable, that means it's more reliable. It's more predictable. That means as the practitioner, you can not only rely on the same employee doing the same steps within the same time frame over and over again, but you've done such a good job in training a multitude of employees to do those same steps within the same time frame over and over again. And that's truly is the job of a Lean Six Sigma practitioner and their team members. You want to be high in repeatability and reproducibility. And you can only do that is by first mapping out what the current process looks like in week 1. And then you make those improvements. You clean up the process, you get rid of the variation, the waste, the inconsistency. You train people on that improved or tweaked standard operating procedures and make sure your employees are following it. That's the exciting part of being a Lean Six Sigma practitioner, that you get to see these before and after results. And how do you achieve that? If we go back to the white belt, well, you achieve that by defining the quality problem, measuring, analyze, improving, and controlling. In other words, you are following DMAIC methodology. Hope you enjoyed this example, and we shall move forward. Changes in standard deviation relate directly to changes in process variation. Sometimes the area we want to estimate appears in a less convenient location. If the limits do not coincide exactly with the standard deviation locations, we will need a more flexibility and precise method of estimating the area probability. The method we will use is actually quite simple. We will identify the location of the points in units of standard deviation. We will find the distance from the mean in standard deviations and look up the areas in a table of areas under the normal curve. The statistic we will use is called Z. Z is simply the distance between the mean and the point of interest in standard deviation. This is getting a little bit fancy, but by the time we go through these slides, I'll let you know exactly what you need to understand, okay? Because you're not doing any of these formulas on your own. You're simply going to be required to enter your data and interpret the final results. No one's expecting you to be a PhD level statistician, because even statisticians rely on statistical software to draw their conclusions. As you can see here, this is the lower specification limits, and this is the upper specification limits. And who came up with these? The customers. Applying what we have learned, what percentage is between the lower specification limit and the upper specification limit? If the limits do not coincide exactly with the standard deviation locations, we need a more flexible and precise method of estimating the area, also known as probability. Standardizing the normal distribution. Z-value, Z-score. The z-value measures how far an observation lies from its mean in units of standard deviation. For example, a selection of factory molds has a mean depth of 10 centimeters and a standard deviation of 1 centimeter. A mold with a depth of 12 centimeters has a z-value of 2 because its depth is 2 standard deviations greater than the mean. The vertical line below represents this observation and its location relative to the rest of the population. mold depth in centimeters. Converting an observation to a z-value is called standardization. To standardize an observation in a population, subtract the population mean from the observation of interest and divide the result by the population standard deviation. The product of these operations is the z-value associated with observation of interest. You can also use a z-value to conduct a z-test. In this case, z-values measure the difference between an observed statistics and its hypothesized population parameter in units of its standard error, which is the analog of the standard deviation when testing the mean. A z-test compares a z-value to a critical value on the standard normal distribution to determine whether the difference between the estimated and hypothesized values of the population parameter is statistically significant. For example, you want to know whether a second group of molds also has a mean depth of 10 centimeters. You measure the depth of each mold in the second group and calculate the group's mean depth. A one-sample z-test calculates a z-value, which represents the number of standard errors that lie between the group mean depth and the hypothesized mean depth of 10 centimeters. So what is the z? It is a distance between the mean and the point of interest in standard deviations. This is how it's written, and it's increasing analytical flexibility. Normal distribution and the z transformation. Let's look at z transformation general form. Application of this equation to data points produces a value from a distribution where the mean equals 0 and the standard deviation equals 1. The values indicate how far the numbers is from the mean in its units of standard deviation. For example, if z equals 2, that would say that the number in question is 2 standard deviations away from the mean. Using this method, we can calculate the proportion of product that is out of spec based on the product's output mean and standard deviations. There's a lot of statistics being thrown at you in order to cover the body of knowledge. But when I get to the point of explaining this to you, that you are not going to be doing any of these formulas by hand, and that even statisticians, even though I'm required to teach you this, even standard deviation, even statisticians who are PhDs do not do these formulas by hand. It's just that you're trying to understand some of the theory associated with this. And the theory that you're supposed to just truly comprehend is as followed, okay? Let's say, for example, you have some raw data and the mean is 1.034. So you're somewhere right here. This is the mean right here. And the standard deviation is about a half point to the left and a half point to the right. Let's say your customer has requirements and your customer's lower specification limits is at 0.9. So let me pull out my highlighter. Your customer comes out and says, when it comes to the raw data, we need it to be at 0.9. So basically what they're saying, if there's any data points that are below 0.9, your process is out of control and you need a Lean Six Sigma practitioner to fix it and get all the data points back into this area. That's all it means. All of these slides, even though they're very like PhD statisticians, and I have to teach that no matter what you need to understand is that all the data needs to fall from this line to that line. And if they do, you are A-OK. You can say that the process is in control, that window glass is going to fit the car, that Brista's in good shape and keeping the customers happy. And that's truly what it comes down to for any process. And if any dots are here, below the LSL, below the 0.9, you're in trouble. You need to figure out where all of the errors are coming from, where the efficiencies are going to come from. You're going to create the improvement plan and get all the dots back between this line and this line. And that's all these formulas are basically telling you in very fancy, high-level PhD statistician language. And so your customer is also coming out and saying the upper specification limit is right here. It's at 1.1. So what's the range? The range is, the customer says your raw number should be 0.9 to 1.1, and that's it. This is the room for variation. And what are you doing as a Lean Six Sigma practitioner? Is trying to reduce the variation as much as you can so you have a tighter process. And you do that by training your employees, and for all employees to do the same steps in the same order over and over again. Hopefully I simplified this for you because there were so many slides, and this is really what you're going to be doing as a practitioner. So don't let this high level equations that no one does unless you are a high level PhD statistician who's going to do this all in, paper. I'll do it by hand. No, the statistical software program is going to do this for you, as you're going to learn about when you get to the black belt courses. But you still got to teach this, okay? So normal distribution and the Z transformation example. You got the raw score distribution and you got the standard score distribution. A lot of the times we transform the data so it resembles more of a normal distribution. We can now calculate the areas below the lower spec and above the upper spec using the normal probability function. Z transformation example. The task is to determine the estimates of the proportion of the normal curve that is outside the upper and lower specification limits. We do that by calculating a Z value for each specification limit. This ain't looking that good, okay? Because this is the lower specification limits, 0.9, and this is the upper specification limits. You see all this thing in blue? These data right here, they're above that limit. That's not good. Your process is out of control. Look at all of this blue area. It's above and beyond that red line. That's not good. A little bit here. Look how much here. Above this line. This is not good. This is a process. If you punch in all your numbers in Minitab, okay, and you have your before improvement plan numbers and your after improvement plan numbers, and you get data that is below 0.9 and below whatever that number was it 1.1 or something like that? That's not good. You see blue. This is a histogram, y'all. If you see blue data points that are above this red line, it's not good. It means your process, you as the practitioner, you still don't have a process that's in control. And that's a problem. It definitely indicates that your project was not up to par or a failure, whatever you want to call it, right? Not good. And these are all fancy things. And what I'm telling you is what you're going to have to know is that when you're in Minitab, you're basically going to enter all of the data, like your before improvement plan numbers and your after improvement plan numbers. And then they create this output. And what you need to understand when you are copying and pasting this output, that if you have data that's above this red line, that your process is not in control. And it truly is that simple. No one's going to require you to do any of this on hand. And that even PhD statisticians, they are relying on statistical software, whether it's SPS or whether it's Minitab or whether it's Excel, to do these formulas by hand. And you shouldn't even be doing these formulas by hand because you can make a manual mistake. Okay? Let's close the highlighter. Normal distribution in Z transformation. The fraction outside the specification limits can be estimated as followed. So, whoa, all of this fancy stuff is telling you that 12.48% of the time, the data, it's outside of the customer's requirements. This is a total epic failure. This is not good. This is not acceptable 12.4% of the time. This is absolutely nowhere close to operating at a Lean Six Sigma. Because what did we learn about in the Lean Six Sigma white belts, which you have full access to in this yellow course? Just by sitting this your yellow course, you got all of that white belt information automatically. What did you learn? That if you were operating at Six Sigma, there would only be 0.03 point defects out of 1 million opportunities. And look at here, you're at almost 12.5%. And that's not good. Where do we get these probabilities? One option is to look at the normal tables. The second option would be to use computerized normal tables like those found in Minitab. And I know, like, even though I always have to teach all of these formulas and show you the raw manual way of how PhD statisticians are doing it, when we get to the black belt, you're really going to see it's as simple as creating two tables, entering what your numbers looked like before you implemented your improvement plan. So before you trained your employees on the new process or the tweaked process, and what your numbers look like after the improvement plan. That's truly what it comes down to. You, my friends, are going to learn how to master Minitab to do all the complex statistical formulas for you. And rest assured that even PhD technicians are not doing these formulas themselves, because that would result in a lot of human error. And it would take hours and hours to do these formulas, especially when you're dealing with large data sets. It's good to understand a little bit of the theory behind it, but I don't want you to get discouraged. I don't want you to get bogged down, because most students are going to feel that way. I know, I've been teaching the subject for a long time. Example, Z transform. Suppose we establish that customer price tolerance for a new service. Actually, let me close this lighter first because I have a tendency to keep it open. Here it goes. Suppose we establish that customer price tolerance for a new service is normally distributed with a mean of $400 per socket per month and has a standard deviation of $30. Okay, let's dissect this carefully. It has to be around $400. That's what they're willing to accept. And who creates all these requirements? The customer. You always listen to the customer, right? You wouldn't exist without them. And has a standard deviation of $30, so plus or minus $30. Lower prices lead to a perception of low value. Higher prices are not competitive. That's so true. What percentage of customers might we expect to lose if we offered the new price at $450? We could look at losses, which would be the area above $450. Or let's look at retentions. In this case, we're interested in the percent below $450, so that is our X variables. We set up this problem as followed. Remember, what did we say? That the ideal tolerance for the customer is exactly at $400. So let me pull out my handy dandy highlighter. There it goes. Everything's looking good. This is where the customer is comfortable with at 400 bucks. And what did we say the standard deviation? $30. So what does that mean? Plus or minus 30 bucks. Step 1. We let the computer calculate the Z. This is the upper specification limit. This is what the customer is okay with. Any dots that fall within here, whoa, you're going to lose customers. So here you're at 1 standard deviation. Here you're at 2. Here you're at 3. So you honestly do not want to be above the $430. You really don't. The upper limit is 1.67 standard deviations above the mean. It's right here, around $430. You don't even want to be at 440. You don't even want to be at 450. You don't even want to be at 460. You definitely don't want to be at 490, right? That's not good. Z transform. Determine area coverage. We're looking for anything below the $450 specification limits. So right here, $450, anything below it. This means we have 1.67 standard deviation between the mean, the middle, and the limit, which is USL. And it's 1.67 standard deviations. However, notice that we also have half of the distribution below the mean. See, I'm the type of person, I know I'm not the customer in this situation, but if I can get the same high quality for a cheaper price, let's say there's a good sale going on or something. I know we're talking about sockets in this situation. And I try it and it fits good, I'll go for the cheaper price, right? But let's not get into Sandra's examples right now. But if I can get something a little cheaper, or maybe there's a sale going on or a promotion, I'll still be happy. We are interested in the total area percentage / probability. The area below the mean is 0.5 or 1/2 the total. But remember in this example, they said anything that's a little too cheap might be considered of less value or less quality. How much is covered by the area between the mean and the 1.67 standard deviation? So how much of this area is covered? To find this, we simply look up 1.67 standard deviations in a table and find the area. This is a very standard table that you can look at, that you can continue to reference years to come. I still tell students this is a little not needed, but we're still covering it. To find a 2 decimal Z value, begin with the first 2 digits in the left column and read over to the column representing the final digit. This table shows areas beyond the limit. 1.67 standard deviation, so around 0.05. To find the Z values, look for the 1.6. So it's right here. I wish I had a yellow highlighter, but it's okay. 1.67. Let's see if I can use the yellow one. Let's see what happens. Yellow. Highlighter. Okay, right here. If you guys are following along or you guys want to highlight it, if you guys printed out your PDF already. To find the z-value, 1.67, look for 1.6, and then read over to x.x7. So let's do this very carefully. This is when I wish I had one of those pens. 0.0475. The area beyond the specification is almost 5%. And this is the area right here. Let's use a little pen. Right here, it's about a 5%. Can't even, where's my little pen? I always wanted to, right here. This is the area, about 5%. Calculate the total percentage. To find the total percentage of the distribution under $450, this area contains 4.75%. This area contains 50%. Find the area of 1.67 percentage, 0.4525. Add the area of the left half of the distribution to the area of 1.67, standard deviation, and then you're at 0.9525 because you're adding the 0.5 plus the 0.4525, which gets you 0.9525. With this solution, we lose about 95% of potential customers. Will the added value cover the lost volume? Ideally, I tell my students, as practitioners, don't even get to that point. If your customer is telling you, and that's why I feel like this is a little too excessive, but if your customer is telling you that their ideal price is $400 and the standard deviation is plus or minus $30, and they're telling you this is the range they're comfortable with, or what was it? Was it 400 or was it? Yeah, it was 430, right? And if they're telling you this is what they're comfortable with, plus or minus $30, then you just want to make sure that you don't have anything. Ideally, if your process was tight, you'll have nothing below $370, and you won't have anything above $430, and you avoid all of this to begin with. And that's what you want to do as a Lean Six Sigma practitioner. So basically, get exactly what the requirements are from the customers. Jot down to the lower number, jot down the highest number. If it was plus or minus $30, which was the standard deviation, the amount of variation required, then just make sure you're staying between, like this example, you're staying between, if it was 400, then you would stay between 370 and 430. But if it was 430, then you're staying between 400 and 460. Because I messed up, I just realized the mean is 430, not 400. About 95% of our customers would continue to purchase at this price. Probability exercises for practice. What is the probability of a hold time over 12 seconds? With a mean of 10.5 seconds and a standard deviation of 1.5 seconds. What is the probability that we will transfer an order within 10 days of the customer request date if the data shows our customers able to use data? Relating z-values to Six Sigma. That says that the mean of the distribution is 6 standard deviations away from the spec limit. To achieve Six Sigma, the z-values for the upper specification limits and lower specification limits should be at least 6 each in a short-term capability study. To calculate the optimum sigma possible for a process, add the probabilities calculated to be outside the USL and LSL Use a normal distribution table or Minitab's inverse cumulative distribution function to convert the probabilities to a z-value. For short-term capability data, this z-value directly represents the optimum sigma level. To estimate the long-term sigma level, subtract 1.5. For long-term data, add 1.5 to the z-value to determine the optimum sigma.